No, this is not another DIY CW decoder video. It's worse than that. It's about a way to generate code. Now, before you say I don't give a rip about CW, this project may be worth your attention. Have you ever considered a project where, while the MPU ran your code, a wireless keyboard would serve as control input? If so, I'm going to go over portions of this project that will let you do just that. Now, to be clear, I'm not using an Arduino board, nor am I using the Arduino IDE. Instead, the board in this project is the STM32F411 Blackpill, and its source code is compiled and loaded using the STM32CUBEIDE, both more powerful than the Arduino platform. Yet, we're still looking at essentially the same price point. For example, in the US, on eBay, the Blackpill sells for approximately $11 plus a couple of bucks for shipping. And the IDE can be downloaded direct from the STM website for free. To make this project as cost-effective as possible, I wanted to use a generic Bluetooth dongle and wireless keyboard. Googling to see what others had done came back with many asking how, but most responders didn't seem to get the question, often asking why, or explaining how an Arduino can be configured to look like a US keyboard, when the question was clearly, how do I get my MPU to host a keyboard? Maybe it was really Google that didn't understand the question. Either way, it took some digging before I found that a group of folks had indeed attacked this issue, and better yet, had posted their collaborative effort to a GitHub site known as USB Host Shield 2.0. Their project is built around the Max 3421E breakout board, and today there are several variants of this shield on the market. Among them is the mini version for $7.50, which is perfect for the 3.3 volt F411 Blackpill. I also found a second GitHub site, Nucleo F446 USB host, where many of the underlying files needed to run the first repository on the STM32 platform were ready and waiting to be used. I had already done much of this work, but have to confess the second repository contained at least one workaround that I hadn't completely worked out, specifically an implementation of the serial class and its many type transformations. We all take for granted the plug-and-play concept that USB brought to the computer world. Prior to its appearance, every time something new was connected to a computer, the user could expect to spend hours sorting out how to get the new device to work. But USB hosting is built around the host having access to essentially an infinite set of drivers that can be queued up on demand. Adapting this to operate within the tiny, by computer standards, fixed program space that most Arduino-like MPUs have means scaling back exactly what can be plugged into the MPU's host connector. In my case, all I wanted to accept was a Bluetooth dongle, but negotiating and hosting a Bluetooth connection creates a whole other set of possible responses. The Bluetooth 5.1 core spec is close to 3,000 pages. So again, running this on a Blackpill meant it had to come with restrictions. So to be clear, this application only accepts the wireless keyboard class. Nevertheless, when you launch a Bluetooth inquiry, all kinds of devices can show up. So the code must have the wherewithal to pick through those finds and select the keyboard while ignoring everything else. Here I have access to 3 dongles, an old IOC 2.0 Broadcom dongle and 2 CSR 4.0 units, versions 7558 and 8891. This project works with all 3 and the one 3.0 Bluetooth keyboard I have, but that's as far as my experience goes. So stick with these or be prepared to have an adventure in programming. On the good side, the code is rich with debug output, and the STM32CUBEIDE supports breakpoint debugging. The bad news is just because you stop the code doesn't mean the Bluetooth process stopped. So often it's better to catch the events on the fly and then do a post-mortem on the results. Now, let's switch gears and look at the project as a CW generator and what it has to offer. First, it's pretty basic. For example, it doesn't have a bunch of programmable memory features, but for basic sending, it works pretty much as you'd expect. Press a letter or a number key, and the character appears on the screen, and the appropriate Morse equivalent is generated. The typing is buffered, so if I type faster than the send rate, the text appears on the screen as fast as I type, while a moving backlit cursor shows the current character being sent. As long as the character on display hasn't been sent, it's possible to backspace and delete the buffered text and re-enter new text, but it doesn't support running the typing cursor back and inserting text in the middle of buffered text. The feature is possible, but hasn't been implemented yet. A few keyboard symbols that don't have direct Morse equivalents, like the plus and equal, have been set up to send some of the commonly sent special CW codes like BT and KN. Of course, if you want to add more or reassign the ones already in place, you can modify the source code. Speaking of modifying the code, you'll probably want to modify the myCall variable found in the keyboard R01 CPP and replace it with your own call sign. Once done, you can send your call by pressing the Enter key. The last special function I want to point out is the Control+T keys. Pressing this key combination yields a continuous key down condition. On some rigs, this is needed for tuning. Press Control+T again or any other key, and the keyed output is restored to normal operation. As I said, it's pretty basic, but should serve a casual operator fairly well. Now, the last thing I want you to be aware of is wireless battery-powered keyboards go to sleep after a period of inactivity. On the TFT display, you'll know this to be the case by a yellow status message at the bottom of the display. To get things running again, press any key, but the caveat here is it can take a second or two before the Bluetooth connection is re-established, and until that happens, no keystrokes will be captured. This is a good segue into the connection process itself and how it works in this application. So let's start the Blackpill and note what happens on the display. Behind the scene, a lot's going on, so much so it's not practical to show everything. What I've tried to do is distill it down to what's needed to give a sense of what's going on. To be honest, the system is not bulletproof and can get locked up or lost. The blinking blue box at the bottom of the screen is your reassurance that the program is at least running. The unit can be powered up with the dongle plugged in or not. Once it figures out there's a valid Bluetooth dongle connected, the status line will read Enable Discovery Device, meaning it's time to energize your keyboard and press the connect button. When the dongle finds the keyboard, the TFT status line will prompt you to enter via the keyboard the pin number. Enter it followed by the Enter key, and if entered correctly, the status prompt will turn green and read HID paired. At this point, you're done, and the keyboard is now a CW generator. If the pin fails, you need to either unplug and plug the dongle back in or restart the program. Pin entry is usually not where the process runs into trouble. If there's going to be a problem, it typically happens in the discovery phase. Now that we've covered operational basics, let's move to the output hardware. Like all projects in this series, I've tried to find a cheap, off-the-shelf solution. that ideally requires no soldering or keeps it to a minimum. What you see here works for my needs, but your rig and setup may warrant a different set of components. The Blackpill, as configured, has two keying pins, C13 and C14. They operate in complementary fashion. That is, when one is high, 3.3 volts, the other will be low, ground. The Blackpill is a 3.3 volt IC, and unlike blue pills, don't have 5 volt tolerant pins. So when interfacing this board to the outside world, you need to be mindful that the board's pins aren't connected to something that will violate the pin voltage limits. The little tone board I used will output a tone when its control pin is grounded. Conversely, there is no tone when the control pin is high or open. But if the control pin is connected directly to the Blackpill's 3.3 keying pin and USB 5 volts is used to power the tone board, the control pin will behave as if it were grounded, and the tone will be present continuously. So to get around this dilemma, I added a 2N2222 to act as an inverter and level translator, and used the Blackpill's high-going key-down pin. Now, to key a generic transmitter, I looked for a cheap solid-state switch and found this MOS breakout board. Out of the box, it conducts when its control pin is high, but open circuit, it's rated at just 36 volts max. So beware that some tube-type transmitters may have higher voltage at their keying connections. If that's your case, then look for another solution, maybe a 5 volt relay. To drive this MOS switch, I simply took the switched output applied to the tone board's sonic transducer and connected it to the MOS switch input. This adaptation meant that some soldering was needed on the tone board. I soldered two leads at the transducer terminals, ground and switched 5 volts, and connected them to the switchboard's ground and control pins respectively. Next, I soldered the 2N2222's emitter and collector leads to ground and the board's original control input pin, and finally added a 10K current limiting resistor in series with the 2222's base lead. The other end of this 10K resistor serves as the new input pin. It's crude, but for my station works reliably. Again, your rig and setup may have different needs, so consider what you have before blindly following what I've done here. Now, for those interested in using components of this project in another Blackpill keyboard application, I'll try to give a quick overview of what's in this project that would be useful. But first, let's look at the layout of the IDE itself. On the left, there's a project tree. In the middle is an edit view of the files you have open, and on the right is an outline view of the key components of the file currently being edited. These three views simplify finding what you want when it comes to editing code. And while we're talking about finding things, Control F, the standard tool for finding text strings, is available here, and it has a number of easily set options to further filter what you find in the open file. But often with projects of this type, you'll want to find a term that's used outside the file you're currently in. For that, the IDE has a flashlight icon tool that searches the entire project. Its results are shown in its own tree view. Clicking on an entry in this tree view will open the respective file at the line where the term appears. This tool also has a number of options for filtering the search, admittedly one of my most appreciated features in this IDE. Now, let's drill into some specifics of the project. Back on the left, and at the level of the project tree, there are three entries that I want to drill into. Under Core, there's the Source and Include branches, and then moving down the tree, there's the Libraries branch. Arbitrarily, I'm expanding the Source branch first. Here, there are just three files that need understanding. The keyboard R01 CPP contains the main program loop. This file also initializes most of the variables the F411 hardware, and finally host the interrupt processes used in the project. The main loop itself is really quite small once the program is up and running, but it starts out by initializing and confirming that the MAX3421 USB board is running. The CWSendEngine.cpp file creates a class or object that handles all the processes needed to generate the Morse code. So unless your project is also going to send Morse code, beyond looking at how it interacts with the rest of the project to pass parameters and start-stop the CW processes, you can pretty much ignore this file. Finally, we come to the TFT messagebox.cpp file. If your project includes an LCD display like what I'm using here, you'll probably want to pay attention to this file. It creates a class object that allows you to treat the display like a box that you can send text to. The class object itself handles the rest. By that I mean it has methods that can be called to add text to the display, and the code inside the class will append the text to what's already on the display. The method or function also allows each character group to be colored to suit the application's need. When the text added exceeds the display space, the text will scroll up the page a line at a time. If your application needs a different page size or location on the screen, you could go into the file's code and change the parameters that set these features. The class also contains a separate caller method for the text that appears on the bottom line. In this project, it's the display status line. Again, there's nothing about this file that can't be modified to meet your display's needs. Now, let's move our attention to the include branch. Expand it, and you'll see the companion source header files. They're pretty much what you'd expect. What I want to focus on here is the keyboard parser.h file. When there's a keyboard event, this is the file that you'll use to direct what happens in your application. Notice near the top I've added an entry, define debug parser. Uncomment this entry when you want to determine exactly what happens when your key of interest is operated. Once understood, it's fairly simple to write the code needed to pass the event to the rest of your application. Now, moving to the libraries branch, this is where the magic lives. Most of what's here was ported from the Arduino IDE. And to be clear, a lot of what you see is not used in this application, but is included ready to go if needed. In my mind, this collection of files has two layers. Top layer, usually the files found when you open up any one of the first subdirectories in the library subset. These files mostly contain the code needed to set up and manipulate the respective hardware the library supports. To do this, often specific MPU I/O pins are needed. Because the files came from the Arduino IDE and were written to support a number of different MPUs, you'll see sections of code grayed out in this IDE. That's because here only the F411 is supported, so they're not relevant. Now, the second level that I referenced to earlier can be found tucked here in the utility folder. This collection of files mostly exists to support function calls unique to the Arduino platform. Because the top-level library files often call these special functions, it simplified the porting process to include this utility group, and where these files need to touch the F411 MPU, make appropriate mods there. To do that, I used a combination of STM HAL calls and generic register manipulation compile calls. Some programmers disdain the HAL calls because these calls often perform unnecessary outside operations, where a direct register call can produce the same effect with less code and far fewer clock cycles. Because the IDE is going to make use of HAL calls to initialize the system, I'm agnostic about which way is better. So, not wanting to turn this video into a forum to debate programming strategies, we'll stop here and hope that you found parts of this video useful. As always, good luck with your next project.